Well, thanks for coming. And so today's topic is Beyond the Big Bang. So let me start the story actually. So I'm going to tell you the story. And the story begins from here actually. So this is a journey which we took some 400,000 years after the Big Bang. Okay. Now our home is, as you know, that well we live on our planet Earth, it's in solar system, but actually our bigger home is the Milky Way. You might have seen the Milky Way, the haze of Milky Way. Yeah. So we live in one of the arms of the Milky Way. There are many arms. You can see one of the neighboring arms from Earth. Especially if you go to the southern hemisphere, you can have a perfect view. We live in a local group actually. There are plenty of dwarf galaxies, not as big as this. Ours is quite big actually. It's a huge, massive galaxy. We host a couple of small galaxies. It's a part of a Virgo cluster. It's many more system, but it's a bigger system here. Our neighboring, giant galaxy like ours is the Andromeda galaxy, and that forms a local group. And amazing thing happens, as you can see in this video, that some 400,000 years ago, what happened was the matter just collapsed under gravity. So the only thing which worked there was the gravity. The cold matter just collapsed under gravity to form a structure, something very similar to what we see like in the case of Milky Way. You see that the matter is falling in, and eventually it got its spiral arms, its tentacles, and we are somewhere close to here. The sun is somewhere here, which is rotating around this galaxy here with 200 kilometers per second. So we are actually rotating the center of the galaxy. The belief is that near the center we have a giant, supermassive black hole sitting there, whose mass is something like 10⁶ times the solar mass. The solar mass is around 10�33 grams. It's a huge, massive black hole is sitting there. Okay. Now we are not alone. That's the thing which we have realized. So that's the Milky Way. Now imagine yourself, you go backwards in time, but you are going backwards in time with some kind of time machine which is moving with fairly close to the velocity of light. And this is what you see. You see a spherical structure surrounding you. You have passed now this, imagine that you are in kind of like the spaceship. You have passed some of these dwarf galaxies which we have mentioned. Soon you would see our biggest giant Andromeda passing by. And you're probing backwards in time. You're going backwards in time from now. Okay? Now keep in mind that the velocity of light is something like 3 times 10⁸ meters per second, and the distance which we are probing is something like 10⁻26 centimeters. It's a huge distance we are probing. Our universe is something like 10⁻17 seconds old. Okay, so that's the thing which we realize, that we are not alone. There are Milky Ways like galaxies are plenty actually, and soon you would see the galaxies emerging from the from all the different sides. So you see this typical galaxy. It's not quite like ours, but it has its its own similar kind of features like ours. Some of them are some of them have a spiral arm, some of them don't. And as you go backwards in time, you see more and more galaxies are zooming through. Yeah. And what we have done, that what we could see only as you would see that there are slices, the slices of galaxies which you could see. We have not even explored the entire spherical system. It's actually quite expensive to do it. It's not so easy. I mean, you can't do it in just 1 year or 2 years. It's a huge program. It takes a couple of years. Now you can see what we have explored here is a handful of slices in this entire sphere. And you see billions of galaxies like ours are sitting in here. The galaxies form the clusters of galaxies, the superclusters of galaxies. There are voids in between. So it's a large scale structure which we are talking about here. And this is a subject which we would like to understand, that how the galaxies are formed, how the system has formed from the very beginning. Yeah. And as you could see that, by the way, these are just the galaxies which you see. These dots are just the galaxies which you see. Is just within our neighborhood. We have not even explored the entire our past. We have explored only a small fraction. I mean, the furthest galaxy is sitting somewhere here. whose age would be roughly comparable to the age of the universe, maybe 1/10 of that age of the universe of 10^17 seconds. So we haven't really explored the very far end. It takes even longer time to explore them, and the background, what you see is that we are kind of like smeared in a cosmic microwave background radiation. It's the radiation. Once you go out of the space, go out of the Earth's atmosphere, you find that it's a very cold, chilled place with a temperature of 2.725 Kelvin. This is known as the relic radiation coming straight away from the Big Bang. And that's the thing which we have seen very recently. We have measured the small fluctuations and things like that. So hopefully this will, this tells us that we are not alone. There are plenty of galaxies like ours, plenty of stars like Sun, and plenty of habitable zones like Earth are present in our own universe. So there are a couple of, we have a couple of big questions here. So the first question is that, how our universe began. That's the query which perhaps the mankind always had this, from our ancestors had it, now we are having it. And I'm sure even 500 years from now or 5,000 years from now, people will ask more or less similar kind of questions, because as the technology advances, you ask much more deeper questions, because you have the availability of, deeper and deeper insight about our nature. So was there a bang, or was there a universe before the pre-Big Bang, before the bang, or in a sense, like, was there a universe already existing, or just we had just one single universe? Or even if our universe, how the universe began and how it became so big. As I've shown you the length scales, we are talking about something like 10^27 centimeters. That's roughly the observable length scale. Of course, the universe doesn't have a boundary, but that's the kind of like visible, visibly you can feel, you can see the universe in various different spectrum, electromagnetic spectrum. And you perhaps I think in one or two lectures before, someone might have spoken, I think Laura might have spoken to you about the electromagnetic spectrum. So the question is how the universe became so big and so old. Yeah. So you see that nature knows how to play the dice. Now if I play a dice here, I can play only finite number of times, because my lifetime is very short. Maybe I would live for 60 years, 70 years, 80 years. But the nature had 13.7 billion years to play dice, and as many times as per second you can think of. So nature knows how to make the all sorts of diversification which you see in the nature, the huge structures. So nature had time to play with. So that's the big thing about nature, that is, it knows how to do it. Just because the universe is not just a second old or 2 seconds old or a year old, it's 10^17 seconds old. What fuels the universe? Yeah, how long can we go on like this? That's the question that we always wonder. And are there parallel universes? Are there many universes? Are they perpendicular? Are they going to collide with us, or will they collide with us? And there are always these kind of uncertainties. And how many? The last question, perhaps, which I will shed some light here, was how many habitable zones are there in our own Milky Way? And at the end of the day, I will tell you that maybe in far future, not immediately, maybe 5 billion years from now, maybe we'll have to think of even these questions. We have to think very seriously, because there's going to happen some cosmic cataclysm which will actually affect the human civilization on Earth itself. So we need to think about these questions perhaps from now. So with this, let's start the quest about the connection between inner space and outer space. It's very well interconnected. Now you may think that you have heard about the subatomic particles. Yeah, they're very small. Roughly, you're talking about roughly the size of an electron, or the basic fundamental particles. Roughly, you're talking about the length scale of 1 part in 10^13 centimeters. And here you're talking about, in cosmology, there's huge length scale of 10^26, 10^27 centimeters. Yeah. So there is an interplay. So in order to understand the universe which you see today, you need to understand the subatomic particle as well, their interactions, how they're interacting. Yeah, so there's a kind of deep connection between these two length scales. Yeah. So whenever we talk about cosmos, in spite of the fact that we are dealing with very big distances, at the end of the day, at the level of fundamental level, you need to think about the subatomic physics as well. So perhaps I think in your last lecture you might have heard about that all the interactions of nature governed by the four forces: electromagnetism, like I can see you, you can see me; the weak interactions, which we don't feel it, but it's fine, we don't feel it, it's okay; nuclear reactions, which we actually, in a way, we feel it. The fact that our body, we are stable, is precisely because of the nuclear reactions that are going on constantly. The nuclear force is binding us. That's why we are alive, actually. The gravity, we all know that, and we in the first movie, as we have seen, that because of the influence of the gravity, these structures have fallen in to form the galaxy. All this is one of the weakest force of nature, but it plays a very important role. And perhaps you have also heard last time about something about the Large Hadron Collider, which is which you might have heard about news from BBC or from newspapers. It has caused quite a lot of excitement to the scientific community, and especially to Britain, because one of our great physicists, Higgs' name comes in always whenever we talk about Large Hadron Collider. So you see that this is roughly, you can't perhaps read this part, but this is roughly, the mankind have reached the energy to explode the universe somewhere here. We are somewhere here, actually. This is the part of the physics, part of the fundamental subatomic level physics we are exploring here at this point, yeah, with the help of this machine. We have a long way to go, but there is a hope that maybe we can actually understand some aspects of the Big Bang, or even beyond Big Bang, by understanding some of these machines like this. Of course, these are very expensive machines, but nevertheless, the quest always has to be there, and the endeavor has to be there. Now, just to give you an example, that you have used the batteries, 1.5 volt batteries actually can accelerate an electron with an energy of 1.5 electron volt. So just to give you an idea with the numbers, how we play with the numbers, is that the LHC is working at this scale, 1 TeV, which is roughly 10 raised to 12. So almost 10 raised to 12 times the power of the battery, which we have here, 1.5 electron volt, 1.5 volt battery. So that's the energy through which it can accelerate the particles. And the largest energy which we can ever think of is something around 10 raised to 28 electron volt, where we believe that all the forces of nature merge, including the effect of gravity, merges with all the rest of the three forces of nature. They unify together, and that's the kind of like beauty we always believe in. We believe in some kind of like unification, and because part of the reason is because of the symmetry principle, because we are blind, we don't know, we are just probing something in darkness. When you want to probe something in darkness, what do you need? You need a measuring stick. You need a stick to go on, yeah, to make progress. And for us, for the one of the things which is very important is some of these symmetries, some of these beauties. We love beauty, and that's the thing which drives us to go and explore the physics beyond the energies which we have right now. Okay. So if you want to see the lifeline of our universe, we are somewhere here. We are somewhere here. Our temperature, as I showed you, permeated by this cosmic microwave background radiation, which is roughly at the 3 Kelvin. And you can go backwards in time. As you go backwards in time, the temperature of the universe, so these are the color gradients, which shows you the temperature. The temperature of the universe increases gradually and becomes here. By the time you come here, it becomes so hot. You see the 3000 Kelvin, yeah. At the temperature of 1 electron volt. So this is roughly your 1.5 volt battery was working at the time. Actually, that's the kind of energy you were accelerating in the universe. Imagine you have stacked your universe with 1.5 volt batteries, infinite number of batteries, and they're all accelerating your electron and positron, all the fundamental particles which we are all made up of, with the energy of 1 electron volt, and that could actually generate enough heat to with a temperature of 3000 Kelvin that we cannot survive. Actually, human body cannot survive. So we fairly well understand in this chart. I'm not going to go through all the details. You can ask me later on. We fairly understand the universe up to 1 MeV. That's the temperature around temperature of 1 MeV when the age of the universe was roughly 1 second old. So we know how the universe behaved around 1 second old, when the universe was just 1 second old. But now we are talking about even in smaller and smaller fraction of the time. You see 1 part in 10 raised to 11 seconds, 1 part in 10 raised to 35 seconds, and 1 part in 10 raised to 43 seconds. Even smaller time scales we are talking about. And this is the scale at which we believe that all the forces of nature unify at this particular point. Yeah? Now, we roughly know also what is the constituents of matter. The quarks and leptons, these are the main constituent of of everything. Whatever you can see the table, desk, humans, we are all made up of these particles actually. So these are the fundamental particles which we are made up of, and some of the particles we have seen already in nature, but some of them we were very lucky to see Higgs boson this year, and hopefully we'll have a better confirmation by the end of this year, hopefully. But some of the particles we have not seen yet. For instance, some of these for instance, gravitons, for instance, we haven't seen it, but it's responsible for attracting two massive particles, massive bodies. We haven't seen something called dark matter, and you will see towards the end of the lecture how important it is, because if there were no dark matter, perhaps there wouldn't be any form of life actually. The dark matter is responsible to form the galaxies and everything which we see, the large scale structures in the universe. Okay? So as I told you that we are also permeated by this this relic density, relic photons coming straight away from the Big Bang, which has a temperature of roughly 2.728 Kelvin. It has a perfect black body spectrum with a temperature. This is the temperature, this is the intensity and the wavelength. Right now we have the science has advanced to the extent, or the technology has advanced to the extent that not only if we see this beautiful curve, we see a small fluctuation around this curve as well, and this is the fluctuation, roughly 1 part in 10 raised to 5. So there are some patches, you can see that there are yellow patches, red patches, blue patches. So the temperature difference between them is roughly 1 part in 10 raised to 5. So that's the kind of accuracy we are talking about, and we have reached that kind of accuracy. Yeah, and these photons are coming straight away, way back, something like 400,000 years ago. They were created here, and we see them here. We are sitting somewhere here. They have traversed throughout the history of our universe, and we could see these photons coming, and we can measure their temperature. We can measure their the differences from one point to another point, and that's really a miracle, thanks to the advancement of the technology, with what we can do. Yeah. Now, so all these things have established, all these evidences have established something called Big Bang theory. Yeah. Now, that's the place where perhaps there is a confrontation comes with the religion and the science, and that's why I said that you got to be kidding here. Perhaps you know this gentleman. He was a person of the last century. Actually, in the Time magazine, you could see this is the guy who actually shaped the universe and the most influential person of the last century. Once he made a famous quote, which has been used many times in many contexts, that the God does not play dice. And perhaps he was true at the time, and perhaps he is still true. Who knows? We haven't really reached the conclusion. That's the whole saga of science, that you have certain ideas, you want to falsify that idea, and it may take some many years to falsify it properly. Now the idea behind is that following, that this is on your x-axis you have time, you have space. This is your space in this direction, in the horizontal direction, and the vertical direction you have time. We might be sitting somewhere here, somewhere close at this point, some 13.7 billion years from the Big Bang. But when you go backwards in time, as I told you, that the temperature increases. It increases so much at some point that, at 3,000 Kelvin we can't survive. Even beyond that, the temperature of the universe becomes so hot that it melts everything to the just bare subatomic particles. The universe becomes a soup of particles which contains really quarks and leptons and all the fundamental particles which you can ever imagine. Yeah. Now you go backwards in time. As you go further backwards in time, there's one thing which happens, which is inevitable, is that there happens something really very bad. This region becomes so dense that if you plot in this graph, if you plot the cosmic time, roughly suppose you're here, roughly this is the age of the universe. If you go backwards in time, you're probing the universe back, much when the universe was much smaller and smaller, and close to this point, and the energy density of the universe, energy density is something like energy per unit volume. You can calculate the number of people here, maybe 100 people here. You multiply their masses, roughly say 60 or 70 kilograms, say for instance, and take the volume of this room, you divide that volume, you get something called energy density. Usually, the scientific community love these words because what's more important is not only the energy, but also how much volume does it occupy. That's why we call it energy density. We use this concept quite a lot in physics. Now, what you find is that the volume is shrinking, the energy density was increasing, and as a result, everything go bad here at this particular point. We can't imagine anything beyond this point. That's what this gentleman has taught us way back in 1920s. Yeah? And one of his conclusions was that this is going to happen, and perhaps there's no way you can get rid of it. Actually, it becomes a fact. So the universe had to start at a particular instant of time, at a particular point, and from there it evolves to whatever we see today. Yeah. But amazingly, the last century was amazing because the last century, I think, whatever development in science happened over the entire human civilization, I think we have lived almost, believe it or not, as a human species, we have lived almost half of our lifetime as compared to other species on Earth. And but the last century was amazing because so many thoughts came around from so many people all over the world that we made huge advancement in our understanding the nature itself. And one of the aspects of nature, which perhaps someone else will talk here, is about the quantum physics. Now, in quantum physics, it's slightly different from classical physics because there are certain things which don't really, it becomes counterintuitive actually. It doesn't always work exactly in the way we think classically things work. In quantum mechanics, for instance, there's something, this inherent uncertainty. So what it tells you that simultaneously you cannot occupy this, you cannot really tell your position as well as your momentum or your velocity, for instance. So, or you cannot really say what is the instant of time and what is the momentum it has, if it's a moving clock, for instance. So things like that becomes a little bit more fuzzy in a way. There is inherent fuzziness there. There's inherent noise which you cannot beat. You have open, suppose you switch on your television or radio. If you do not match the frequency, what you get? You get a noise, simple noise, the black dots on your television set. That's the noise. It could be a quantum noise. If you go back, if you go explore the system deeper and deeper, you find that there is a inherent quantum noise which you cannot beat. No matter whatever technology you do, whatever advancement in technology you have, you cannot beat this quantum noise, which tells you that, in a way, what it tells you that you cannot really define unique position. So, as you can see in this plot, in this here, I've showed that the universe started at a given point, at a given instant of time. That's the place where the quantum mechanics comes in and tells us that no, it might not be the way we imagine the way our universe began, because you cannot really define a unique point. You're neither here nor there. So the question where you are, in the quantum world. And as you can see from here, that when as I told you, that this is the point actually where the gravity also becomes very important. And when it comes to gravity, although we understand many aspects of gravity, although we understand that how gravity has formed this large scale structures of the universe, but at this particular point, at this instant of time, things become really hairy, because we don't understand how gravity works at such small distances. It could be deceptive. And the quantum nature of the fundamental physics plus gravity could even resolve this kind of singularity in such a way that you could imagine that if you were living here right now some 13.7 billion years ago, if you go backwards in time, somehow you can resolve that fuzz. It brings an inherent fuzziness in your space and time, such that you can actually go backwards and explore the universe beyond whatever you have, whatever we perceive right now. We perceive that this could be our universe, but no, in principle, you can have universe even before the Big Bang. Okay, and that led to many physicists, including Stephen Hawking, to say that yes, indeed, God does play dice sometimes, and not only he plays dice, but he can play in some places where we can't even see it. And of course, there are places like this where we cannot, whatever we do, whatever advancement we make, perhaps we will never be able to explore the physics of this region. This region will remain be kind of uncertain for us. So this is the quantum world. In a quantum world, you bring even the gravity, you can vanish gravity. It's a magic. It's a magic without a magic, I say. Because you can, gravity always leads to attraction. You can do whatever you want to do. You can even vanish completely gravity, and you can have a universe even before the Big Bang. So there could be a cycle. So the cycles of universe could come in. You have a Big Bang, you have a big crunch. It shrinks the universe, entire universe. Then again it expands, and again this cycle can keep going on and on and on. Okay, so that's a possibility. And of course, there are theories, many theories people have worked on where you have this kind of possibility. So you can have universe before our own universe. So let's come back to the next question: how the universe became so big. Yeah. So, or could there be other universes? Could we? Whether we have talked about the galaxy. Our galaxy is not the only one. There are many hosts of other galaxies are there. So now we can ask the question: is there only just single universe, or could there be many, many more universes? Are they going to at all interact? Are they going to collide? Or could there be a perpendicular universe? Could what sort of there could be many possibilities. So let's spend some time on these topics. Now the geometry, the concept of geometry could be deceptive. Here, you're standing here, you're sitting here, you find that the room is pretty flat, the surface of the floor is very flat. But we know that the Earth is not. It's a spherical system. Exactly in the same way, the topologies, if you're a small, like for instance, for this particular example, if you're an insect, you see a very local geometry here, you see that everything is flat, but globally, it's not a flat geometry. Yeah, it's a spherical system. So in this respect, geometry could be very deceptive. So we might be living, the topology of the universe could be any of these. It could be either very flat, it could be very closed, like a spherical system. You imagine yourself sitting on a, suppose, not a two-dimensional ball, but a three-dimensional ball, in the sense like you have 3 dimensions to explore, plus another dimension which is time. Or you can sit on the saddle, for instance. Yeah. So locally, you would think that they are flat because the universe looks it is big. It's very old and it's bigger. So locally, you would think that things are very flat, but inherently there is a curvature. Yeah. And so in this respect, you have to be a little bit careful about understanding the global properties of the universe. So the question is, why don't we see these curvatures? What has why don't we see these curvatures appearing? Of course, on Earth we do see, after a while, when you go up in the sky, you see the spherical system. Yeah, nice spherical system, which is our Earth or Moon or Sun. Yeah, but in the context of universe, you go from here to you go from there. Doesn't really matter. The universe is so big, so old that it looks pretty flat. Yeah. So the question again, this is connected to the question that what makes the universe so big? Yeah. Now, there is a possibility that God, and in this particular case, God did play a dice. Because what happened is that there was an epoch which is called hyperinflation. What it did was that it was caused by gravity, but kind of like anti-gravity. Gravity tries to attract things, anti-gravity will try to repel things, and it repelled to the extent that it made the universe bigger and bigger and bigger. It became so big that not only that you had the one universe, but whoever created this young child here, created many, many bubbles. And it's a possibility. Once you go into this hyperinflation phase, you can actually not only create a big bubble, but there could be many, many bubbles. So there could be, and this one of them could be our own universe. So imagine that this could be my universe. This is the place where I'm living in. I'm talking about physics here. But in principle, there could be many, many universes surrounding us. There could be many, many bubbles surrounding us. Fortunately, we haven't seen them yet. And there are ways which you can actually view them, or you can actually falsify whether they exist or not. Or the one way would be that what happens if these bubbles collide among themselves. Now, thankfully, in our case, we have lived for 13.7 billion years. Roughly the age. That's roughly the age of the universe, and so far we haven't seen any such collisions. So we are quite lucky, actually. In principle, we could have collided with any of these bubbles. But so far, there has been no accidents, because that would leave some undeniable imprint on this. On the sky and the microwave background, which I said that this is the background radiation which we are permeated with. With a temperature of 2.725 Kelvin, with small fluctuations in temperature, we would have seen some patterns like this or this or this, which would have led to believe that in past there might be possibility of colliding two universes and things like that. But so far we haven't seen anything. But you never know; it may happen in future. Of course, when the two universes comes and collide, it's not that it will be huge cataclysmic event. It will be a smooth transition, but nevertheless, I mean, there are more violent activities happen in our universe, more violent than this, and hopefully we'll have some time to talk about them later on. So the third question, perhaps you would like to ask is that. What fuels the universe? Why it's keep running? Why it's keep its expansion? How long would it last? Could it last for a couple more billion years, or would it last for another 100 billion years? So how long would it last? Now here comes the part where we are very ignorant. We are ignorant because, of course, I mean as you can see that our eyes are sensitive to certain spectrum. It's called, I mean, your one end of the spectrum is violet and the other end of the spectrum is red. It's called VIBGYOR, violet, indigo, blue, green, yellow, orange, and red. These are the colors which our eyes are perceptive. Yeah, we can see with these colors. However, there's something which we don't see, and our eyes are not sensitive, and even our instruments are not sensitive yet. So we haven't seen them. They might be passing through us. We cannot feel them yet. It's called dark matter. There are more dark matter than the visible matter. I've shown you this the movie where you could see these galaxies, but you could see that in between they were dark. Now that's the question, that what is this dark stuff is? So unfortunately, even in our own galaxy, there's a large fraction of our own galaxy is made up of something which we don't understand. We haven't seen them yet because they hardly interact with us. If they don't interact, they don't emit any light, and if they don't emit any light or any form of electromagnetic radiation, then our instruments cannot capture them. So that's the true reality, and as you can see, but we have evidences. If there were no such dark matter particles, we would not have existed. And one of the things which I'm going to show you here, that one part of the spectrum is X-rays, and we always go to, we are aware of X-rays whenever we pass through security gates and things like that. We are being X-rayed always. Now you can see that how deceptive things could be. That in optical, this is what you see in X-rays. This was the event which happened, but in optical, you don't see that event at all. Now let me run through this video. You see, in nature, sometimes you have to, like, for instance, our eyes are not sensitive to darkness. Yeah, so you use certain, some device to see. Yeah, so, like infrared cameras, which are sensitive to dark things. Similarly, even in our own universe, certain things can happen. Some events could take place, but our eyes would never be sensitive to. It can only be sensitive to certain different band of electromagnetic wave. And as you can see, what happened in this particular case, we understand the physics actually. The two clusters, heavy clusters, they collided. Yeah, they collided. They rearranged the matter. They rearranged their galaxies. So when you see visibly, you might have heard of Hubble Space Telescope, which has the same spectrum as our eyes. So it's again it's sensitive to the visible part of the spectrum, it just saw the small galaxies here and there. But a couple of years later, the NASA sent another satellite called Chandra, which actually looked the universe in a completely different frequency band, different completely in X-rays. It saw the universe instead of invisible, instead in X-rays, and that's what it saw. It saw that there was some event which took place which displaced the matter, and usually it's called the bullet cluster because you can see the shape of a kind of like bullet which is piercing through the space. So that's why it's called the bullet cluster, the shape of a bullet. It has displaced the matter, and the question is what exactly this matter is which does not shine, and how do we feel its effect through gravity. So these are the questions which have perplexed physicists for ages, and the issue is how do you explain these large-scale structures. I've shown you these pictures. This is one of the slices of the very first video, second video I've shown you. This is one of the slices of that, and you see these are the structures, these are the galaxies, and you see how beautiful it forms. There's a structure, there's a pattern here. There's certain places where dense. So many galaxies form clusters, many clusters form superclusters, and you have some voids, the white places, the white areas which are voids, there's nothing else. So how do you form these large-scale structures? Now, what we believe, the current belief is that these dark matter particles, the dark matter stuff which we don't see, which hardly interacts with us, they're responsible for forming the structures. Now, if you perturb, so what happens is that the normal fluid, like the visible matter, we are made up of some fluid which are made up of fundamental particles such as subatomic particles like quarks, leptons, and electrons, and so on and so forth. They simply fall into the potential well to form these kind of structures which you see today. Yeah, you might have seen the roller coasters. Our young kids, they love to play on the roller coasters. They simply slide down from one hill to the other hill, and this is the same phenomenon is happening. There is some potential well. There's a energy stored. When you take a ball, you just drop it. There's an energy stored in the system. You drop it, it gains its velocity. This is exactly the same phenomenon happening here. So the dark matter, which we don't see, it forms a huge potential well where the matter falls in. And when the matter falls in, it coalesces, it forms more and more, it attracts more and more matter and forms these structures. And this is a simulation which you are running through it constantly in our supercomputers, because these things we cannot do it in, now you can do it even in your fancy laptops because the advancement of technology. But a couple of years ago, we couldn't even do these things without the help of supercomputers. The idea is to understand how this, how do you replicate this picture, and you can see that in this video, you can see some structures formation happening. So this was the beginning, and you see how you form the structures with the voids, with the clusters, and with filaments. So these are the filamentary structures. We join them, yeah, and these are some of the voids. Okay, so the small fluctuations in matter led to this kind of behavior, which actually gives you the large-scale structures which we see in the universe, and has happened precisely because of the presence of the cold dark matter. If there were no cold dark matter, there would not have been any potential, and if there were no potential, the matter, the ordinary matter, would not fall into and would coalesce to form stars and galaxies and things like that. So you asked the question that what exactly are we made up of? This is the cosmic pie. So I have spoken about the ordinary matter. The value actually for if you ask any cosmologist or any astrophysicist, for them what matters is the basic element is hydrogen and helium. These are the basic element. And you see that a very small fraction of that is contained in the total budget. It's a very small fraction of the hydrogen, helium, and other elements which we know, which we are aware of on Earth. There's a fraction of neutrinos. I have not spoken about them. These are fairly relativistic particles. Now we know that they have small, very tiny masses. We have there are experiments which have explored them actually, and that contains a small budget of our total universe. There's a starlight. Stars are giving you energy, and the light, whatever the photons coming out, that contains certain fraction. There's quite a lot of helium and hydrogen. This is the hydrogen, free hydrogen and helium are present in our universe. That is roughly this red part of the pie. The majority of them is the dark matter, 25%, which I have spoken, and beyond this dark matter there is something which we still don't understand very well, which we have realized only recently, almost 10 years ago, and something like 6 years ago. The people, those who kind of like invented or who kind of like discovered this phenomena, got the Nobel Prize. It's called dark energy. It's called dark. These both of them are called dark precisely because we don't understand their origin. And it so happens that the majority of them, you see 70 plus 25, 95% of matter in this total budget is something which we don't understand. We don't understand their origin altogether. So after all, in the universe, what matters is the nothing which matters, you see. Now, again, the legend goes back to this huge character, huge personality. We actually change the shape, change our way we understand nature. And even in his mistake, he actually discovered something which we have understood only recently, the form of dark energy. So this was the man who actually discovered it, who actually gave the concept behind it. So in 1917, Einstein proposed the constant, like you have a velocity of light, which remains constant. It doesn't change from here to there. You go to Andromeda galaxy or anywhere else, it remains an invariant quantity. So he proposed that the universe, actually he was a firm believer in God, and that's why he said that God does not like to play dice. And no one knows, believe it or not, even Newton was, perhaps you know that even Newton was also a firm believer in God. It's just when with the advent of quantum mechanics, we have become a little bit impure in our thoughts. Anyway, so he actually, when he realized that when there was a gentleman called Hubble, he was looking at the galaxies and how galaxies were receding away from us. In 1929, Hubble discovered the expansion. He established that no, universe is not static, it's expanding. And somehow Einstein never felt very comfortable with that fact that universe is expanding. He felt like, if someone could create such a beautiful universe, it has to be static, it has to live forever, and it shouldn't age, shouldn't get older. So he proposed the presence of cosmological constant to counteract actually. But it turns out that when he realized that his colleague in Chicago, Hubble was a great basketball player. He played for the Chicago team actually, but he was also a great astronomer as well. And when he found that the universe is not static, it's expanding, actually Einstein himself said that maybe it was his biggest mistake. It was a blunder. But even in his blunder, in his disguise or whatever you call it, he gave us something, some beautiful insight to us, to the present humankind, that in 1998, the astronomers almost, you can see that the gap of 70 years, astronomers found the evidence for it for the first time, that no, our universe is expanding. It's not only expanding, but it's accelerating. The question was, what leads to this acceleration? What gives rise to this acceleration? And what people realized that is nothing but the kind of constant which Einstein was talking about way back in 1917. So if you have presence of cosmological constant, that would lead to rapid acceleration of the universe not only expands but it accelerates. But if you ask the question, what is the energy density, because you remember I discussed the concept of energy density, it's actually lighter than the water. The density of a water is 1 gram per cc. Our water is amazing, but if you think about some other amazing stuffs, you take our planet Jupiter. Jupiter is actually lighter than water. It can swim. The sun can swim on water. But think about our universe actually. It's even lighter. 1 part in 10⁻30 grams per cc. It's a very, very light. Yeah. So it's really an illogical constant. It doesn't really make sense that it's such a less dense system. How could it lead to such a rapid acceleration of the entire universe, given the fact that the size of the universe is roughly 10⁻26, 27 centimeters? Yeah, so it's a big system. It's not a small system. So that's the puzzle which we are actually, struggling with. We don't know the answer of it, but we have some clue. So the clue is that, after all, what we call nothing does matter. It does change. It has energy. It influences the universe like ours. And it happens again because of this quantum phenomena, because of the uncertainty principle which I briefly spoke in the beginning of today's lecture, that which we think something is nothing, has certainly something, because in the vacuum, you are constantly, vacuum is nonchalant. It's not a static concept. It's changing, it's always changing, and something which we don't understand very well, yet we don't understand, in spite of making so much breakthroughs in understanding the nature, is something where nature actually makes us feel humble. Is this the place where we don't understand how the, in the vacuum itself you're creating particles and it's antiparticle, and how are we, summing up the energy, how are we contributing in our energy budget, we don't really understand. So you see that no matter whatever we do, there is a limit for our own understanding, and perhaps that's the quest which will actually lead us to more and more questions which we ask about nature. So if you take this view that our universe is dominated right now by this illogical constant of nature, which is whose energy density is roughly 1 part in 10 raised to 30 grams per cc, this would be our fate of the universe. So this is the age of the universe, this is the distance, we are somewhere here. Now if the density were larger, our universe would collapse to, so this were the era of Big Bang, and universe could have had a universe before this Big Bang, pre-Big Bang era, and after the Big Bang, universe could collapse if there were enough matter. But fortunately enough, it is not happening. It's not going to happen. We know roughly the fate of our universe is going to expand. It's not only going to expand, but it will expand forever with a huge acceleration, not like this, but just by this. Is governed, its fate is governed by this illogical constant which Einstein discovered way back in 1917. So we are governed by the dark energy, something which we don't very well understand, the nature, the origin. But we know that because of this dark energy, our universe will always accelerate and expand. So what would happen is that the galaxies would recede from each other further and further away, and the density will drop even further. Right now we are talking about the density which is 1 part in 10 raised to 30 grams per cc. It would drop down to hell to 0. Actually, roughly, for all virtual purposes, it would be 0. So we would be only lonely at the end of the day, perhaps. But let's not hope so. Well, if that will take much longer time scale, we have much more things to worry about our own existence. And here comes the question, the last question perhaps of today's topic, and it's perhaps relevant for us, and you can see how relevant it is for us, is that the question you asked, that how many habitable zones are there in our own Milky Way. Our Milky Way is a massive system. It has something like 500 to 600 billion stars sitting in our system. There are as many planets are there. So you ask, this is a very natural question to ask, could there be other planets like us, like ours? Now here on Earth we are very lucky, and that's why we call it, we live in this perfect habitable zone. It's precisely of the water. Water is essential for any life. Our human system is made up of water. Most of the our functions happen precisely because of the presence of water. And it so happens that we are living in a so this is roughly, if you look at the radius orbit, so this is just a unit orbit, if you call it, from the distance from the sun, and as you go further away and away, your distance increases, and this is roughly the size, the mass of the sun, the radius of the sun, the luminosity which it emits energy. So it's, this characterizes our sun, and so in principle you can have, our sun is very ordinary. So it's not that it's a kind of like very typical. It's very typical star. It's not it's very strange star in a way. In principle, you can have all sorts of stars. You can have very blue stars, or you can have very red stars as well. And the blue star could be very hot. If it were very hot, then perhaps it would be very hard to form life. And if it were too cold, perhaps again it would be very hard to form life. So we are in a kind of like a very cozy place where we can form life, and it so happens that you run many, you do many analyses actually, and what you find is that because of the presence of the distance from the sun, because of the presence of atmosphere, because of the presence of water, we are actually well shielded by the sun, and as compared to other planets. But this is not going to, this picture will not remain the same forever, because things are changing. Even in our own system, solar system, things are evolving. And you will see, I will show you a couple of plots from now, how our system our own solar system evolves, and it will evolve in a very dramatic fashion. And that's what led us to this kind of question that, are there other planets which could harbor life like ours on Earth? Yeah. So so recently, well, a couple of years ago, 5 years ago, there was a mission called Kepler, after this gentleman called Johannes Kepler, who actually, spoke about the dynamics, how the Earth moves around the Sun before Newton, and Newton kind of confirmed it in a firm footwork of gravity. But this was the gentleman who was first credited to understand how the seasons change, how essentially how the Earth moves around the Sun, and so on and so forth. Now you can see here, so this was the mission sent by NASA. It's a satellite mission which went up to look for other habitable zones. But look at our galaxy. It's a humongous system. It's a big system. Even with this satellite, we could only explore a very tiny region of our own galaxy. Here we are sitting here. So we are looking for planets. It's a very mediocre effort, but nevertheless it's a good effort from us that this propels our government to actually fund more and more to look for planets into the entire system. But anyway, the way we see other planets is one of the way you can see it through, let's run it back. You see that there's eclipse. There's a planet passing by the Sun, or a Sun-like system. It could be another star in our neighboring system, and if there is a planet passing by it, you can measure the time period, and you can say that, and you can look at the brightness of the system, how the brightness is dipping here because of the eclipse, and you can say that, oh, there is a planet which is passing by. Now, so far people have actually, this Kepler mission has found many planets. And you can see that with various sizes. They come with various sizes. They could be giants. Many of the planets are very interesting because they have two suns. So they are in a binary system. The majority of planets which they have found in the kind of like binary system. So you see these Hollywood movies, and that's the reality. There are there. The systems are like this are there. So anyway, so we have seen many planets of Earth-like system, super Earth, bigger than Earth, Neptune-like system. Even giant planet, 66 to 22 times the size of the Earth alone, and it's just a catalog. These dots are just the planets, okay? And they could, the question remains is, out of these planets, how many of them can really harbor life? And if you ask life, what kind of life they can harbor, and what kind of system they have, what kind of intelligence system they have. Now the question of intelligence is very murky, because sometimes we think that we get fooled that, we think that, we are talking, we are the most perhaps intelligent people, but that's not the case. The intelligence comes completely in different form actually. It depends on how you can adapt in the system, like there are lives in very extreme conditions. So these things we need to bother, and part of the reason we need to bother about because what's happening here, so this is again our Milky Way. Our Sun is sitting here in one of the arms. It's sitting here, and it's actually rotating around this galactic center. And as I said, that there's a massive black hole sitting here, whose mass is roughly 10 raised to 5, 10 raised to 6 times the Sun, the mass of the Sun itself. Now people have done various analysis, and one of the analysis which tells us that in order to harbor life, there are many ingredients which goes into. You cannot be very close to the center of the galaxy because there are many activities going on. You cannot be, so these are the arms actually where you have neutral hydrogen, and when you have neutral hydrogen, they cool and they form more and more stars. So you can, at best, you can be in places where you can form more and more stars, and if you can form more and more stars, you will inevitably form more and more planets. So this is the range. This is the range, outer rim of our galaxy. There's a very good chance that you may find more and more stars. You may find more and more young stars, like our Sun is kind of like youngish, more and more planets. Now, also in the case of Sun, our Sun has certain kind of metallicity. It's in the sense like it burns carbon, nitrogen, oxygen cycle. Now that's what also is very important. Now some stars could be too metal rich, some stars could be too metal poor. Yeah, in those regions you cannot really form system like our Earth. And there could be system where, because in order to form Earth, in order to form our own solar system, it took some time. It didn't happen immediately. So there are constraints. There are various constraints you can put in. This is roughly the time. This vertical axis is roughly the time axis, and this is roughly the distance from the center of the galaxy. Okay, so 1 parsec is roughly 10⁻⁷ centimeters, just to give you an idea that we are very far away from the center of our galaxy. So the life from forming here, it would be very hard, but there is a range where you can actually form life. And it so happens that our sun is sitting actually in this green region, where actually it has enough time to evolve to form planets and life on Earth, and it's away from the center. There's another danger, that you would not want to be very close to very massive old system, because the old stars could actually form something like supernovae. Now supernovae bursts, you can see it from your naked eye, because all of a sudden, even in the day sky, you could see another very bright system. Now once you have this kind of this called explosion, the star explodes essentially, and it releases a huge amount of energy. If this huge amount of energy comes on Earth, our own magnetic field cannot really shield it. So if you have bombardment of such very high ultraviolet rays, actually it is not good for our Earth or good for the life system, because that will immediately destroy everything. We are protected precisely because of our own magnetic field, which I think Jim will talk about very soon, I think, and also because of our atmosphere. Yeah? So there are various ingredients which has gone into forming life on Earth. So you don't want to be very close to these systems. You have to be fairly away from the system, and these systems are present very close to the center of our own galaxy, because most of the stars are quite big, quite violent, quite old, are sitting here. They were the ones which formed in the beginning, and later on our own galaxy started taking away matter from the rest of the system, and these are the neutral particles, the cold part of the galaxy, where you form new and new stars. So you see that there are many ingredients which goes into the system, and it's only recently we have understood some of these. Still there are many more subtleties involved into understanding how really life has formed on a system like Earth. Now our sun, our beautiful lovely sun, is not going to be like whatever we see today. Yeah? In the time span of something like 3 to 4 billion years from now, it's going to change its shape. This is our sun, this is our Earth. Yeah? In 4 to 5 billion years from now, our sun will become bigger and bigger. It will become a red giant. Yeah? It will become so red giant that its surface will come very close to the surface of this Earth. And that's going to happen. That's roughly the future. We know how our sun is going to behave. And it's not going to be good for our own life on Earth, because our Earth will go through various transitions. If the sun's radius comes very close to ours, there will be a huge bombardment of ultraviolet rays, which would actually end up destroying life on Earth. And it's going to happen in the lifespan of 4 to 5 billion years from now. But think about this possibility. This red dot is our solar system, and that was the Milky Way. And that's the time, 1.92 giga years from now. And this is what we are predicting our future, unfortunately. We are in a gravitating system. Gravity always attracts. And as long as it attracts, even in spite of the fact that the entire universe is expanding, accelerating, but we happen to have a very big galaxy sitting very close to us, Andromeda galaxy, and with Andromeda galaxy we are going to collide in 4 to 5 billion years from now. And you see how the solar system will behave. So the lesson we learned that, yes, it's good to keep looking for habitable zones, not only within our own galaxy, but beyond our own galaxy. But that's going to be very impossible. It's not going to be so easy. If you want to see this video, you can see this is our Milky Way. The sun is rotating. Yeah, it's rotating quite fast here. It's just a video, it's just an animation. But this is a real life simulation. People have done it, actually performed it, to see how these two systems behaves. And so we are attracting this local group, and eventually there will be a collision, and as a result of the collision it will completely destroy the solar the solar system. It will be thrown apart completely. You see, this is a cataclysmic phenomena which is going to happen in 4 to 5 billion years from now, and it has been happening. And this is one of the things which we have shown. We have seen very recently, as I've shown you, that when the two clusters of galaxies, in that particular case, many galaxies actually collided, and we see the trace in different wavelength. So it's a part of nature. I mean, it's going to happen. It's inevitable, and so the question is what we can do about it. Well, the only thing which we can do is to have a great escape. Recently, we were very fortunate. We realized that even we always think about sending rockets from Earth, yeah? So how does it work? Because it has to have sufficient velocity to escape our own Earth's gravitational pull. And there are systems, something similar system like that. These are cannonballs. They're huge. These are stars which are moving away from our own galactic plane. Somehow they have escaped the gravitational pull of our own galaxy, and they're moving away from us. So this is the only way perhaps we can actually do intergalactic space mission. I mean, of course, in science fiction you see that many amazing things can happen, but to ask a question that really can we do intergalactic travel is going to be really hard unless until we get hold of one of these stars, because you have to escape the gravitational pull of your own galaxy, and you require huge velocity to do that actually. So maybe there is a glimmer of hope. So the idea is that maybe the human civilization will perhaps go on and on. Hopefully, with the advent of science, the more we see our nature, the more we understand our nature, we can actually find our own way to survive. So let me stop here. Let me end here with a positive note that never stop funding fundamental sciences. That's important, because maybe 1.6 million years from now, we'll be in a completely different place altogether. Okay. Thanks. Thank you very much.